We are here today to discuss a very fabulous Paisa Vasool chapter, and the name of the chapter is chemical bonding. Last week, we underscored the importance of the significance of chapters like atomic structure, periodic classification, and thirdly, I think it was the chapter on volumetric analysis and mole concept. Now, if we take the quantum mechanical progression from atomic structure to be the massive breakthrough in chemistry that gave us all modern conveniences like LEDs and transistors and microcontrollers and so on, pretty much everything, all the modern conveniences from computing devices to cell phones to pretty much everything, including superconductors. Now if we consider atomic structure to be that crucial breakthrough, that would be the cause, and the storm that it created will have to be the consequence, and that consequence happens to be chemical bonding. Now if quantum mechanical model happens to be an enigma, a really tough or difficult concept to wrap your brain around, then chemical bonding happens to be the slightly I wouldn't say dumbed down, I would say rather the more understandable, the more approachable, the more graspable explanation to what goes on inside an atom, what goes on with subatomic particles like electrons, protons, whatnot. So the point I'm trying to make is that chemical bonding is a natural progression from atomic structure to periodic classification, and from then on we go on to chemical bonding. So this chapter is pretty much the whole logical framework behind all of chemistry. Now when I say all of chemistry, sure, there are chapters like solid state, or chapters like thermodynamics, for instance. Maybe not even solid state, even that is dependent on chemical bonding, but maybe thermodynamics, where you can have abstract concepts like entropy, enthalpy, free energy, and so on, even without going into the specifics, the structure of how a chemical molecule is. So that kind of chapter may not depend on this, but then pretty much everything, almost all of inorganic, and to a large section even organic chemistry, it depends on your understanding, your ease, and your comfort level with this chapter called chemical bonding. So straight up, let me tell you, this chapter is very simple. Now that is not to say that it is actually easy. Simple but not easy. So what is not easy? So what do I mean by that? Probably you need more practice, and one of the most big handicaps as far as chemistry as a subject in terms of your syllabus, or for that matter your syllabus of JEE mains as well as advanced, happens to be that we start with chapters which are very difficult, which are very abstract. Now these are chapters like atomic structure or even chemical bonding for that matter. These chapters, your understanding of these chapters will progress, will improve over time. So many people, when they pick up a book and they look at the previous year questions that have been asked in competitive examinations, they get disheartened, and they feel that probably I'm not making inroads into this chapter, so maybe I'm not good at chemistry, and such misconceptions or misplaced assumptions tend to happen because these chapters are not the chapters that you like read once and then you're done with it, you are good at it. No, that is not what happens. So as you progress more in chemistry, as you come to face with many chapters, so as you develop your understanding of chemistry, the different aspects of chemistry, for instance your understanding of acids and bases, your understanding of hydrogen bonding, your understanding of a chapter called solutions, which is in fact in physical chemistry, when you put a solute into a solvent, will it dissolve? If yes, to what extent or why? Or if what is the effect of temperature on the solute, why that is the case? So what reason, for what reason does an ionic solid like NaCl dissolve in water, and yet you have a covalent crystalline compound like sugar dissolving in water as well? So how do we explain that? So many different facets of chemistry, many different areas and ideas of chemistry are deeply interconnected, and some way they all all roads, they lead to they say all roads lead to Rome, but here I would say that all roads are leading to this particular chapter called chemical bonding. Let me substantiate that. For instance, in organic chemistry, so you have this concept called hyperconjugation, where basically, let me say, you have the carbon of a benzene, it is attached to another carbon that happens to be a methyl group, and these 3 carbon hydrogen bonds, how they interact with the pi bond or the pi electron cloud of the benzene ring, so to speak. Now that happens to be related to hyperconjugation. Probably modern chemistry terminologies may have changed, but this is also related to how a banana bond is there in boron or diboron for that matter. So the structure of compounds, how different atoms come together to form a chemical compound. So for instance, you have water. It is once again a result of hydrogen and oxygen coming together. So hydrogen burns in oxygen to give you water. The result of burning being water. That's very strange and abstract. Put that aside, and you have another hydrogen oxygen compound in hydrogen peroxide. Hydrogen peroxide is supremely dangerous, especially highly concentrated hydrogen peroxide. If it is near you, you should probably run away from the place. Using peroxides in organic chemistry have constantly been a challenge even for the most gifted chemists. I think one of probably a Nobel laureate. I'm just trying to pull the names out of my from the top of my head. Probably Sharpless oxidation. That scientist whose name is Sharpless. So he probably, I think, used a lot of peroxide, and I remember coming across one of his mentions where he casually drops in saying peroxides are they are just crazy, they just explode without any reason. So hydrogen oxygen, you have water, very stable. 60 to 70% of our body is water, 65% of the planet Earth is water, but hydrogen peroxide not so stable. Same elements coming together, different structures, different properties. One puts out fire, one is super stable. It's very difficult to actually break the bonds of hydrogen and oxygen in water without using electricity or any something like a microwave or something high tech. If you just have to use fire, it's actually going to be difficult. You may get it to evaporate easily, but it's very difficult to actually decompose and get it to become oxygen and hydrogen. That's not as easy as as you can do with maybe hydrogen peroxide. So same elements coming together, different properties. Why? So your understanding of chemistry largely depends on the fundamental topics of this chapter called chemical bonding. So if you understand bonding, it gives you a very good deal of intuition to be able to approach many different seemingly disconnected areas of chemistry with a confidence and even clarity. I would say more than confidence, I think clarity definitely beats confidence any day. So let me just speak more about this. Yeah, so this chapter happens to be very large. So if you look at the number of concepts, it is just too many, in fact. And like I said, probably if you straight away read this chapter from a book, and try to solve questions from previous competitive examinations, you might feel overwhelmed because you are just beginning. So this is your 3rd or 4th chapter, and you have quite some distance to cover. Probably you have a year and a half, maybe more. So there is a long way to go, and many questions which actually should be classified from different chapters, they are also classified into they also are considered to be part of chemical bonding, because like I said, this is the root of all roads do lead to this chapter. So probably when you look at oxygen group, oxygen, sulfur, and selenium, tellurium, polonium, that group 16. So when you look at the chemical and physical properties of or rather the trends of hydrides in that group, then you invariably come at hydrogen sulfide, H2O, H2T, H2, and H2SE, and so on. So you have trends in terms of reducing nature, trends in terms of central element hydrogen bonds or bond strength, bond angle, reducing nature once again, and stability, thermal stability, and so on. So there are plenty of trends involved, and almost all trend related questions should, logically speaking, come from that particular chapter. But that is not what happens. What happens is they might ask a very quirky question saying which has the lowest boiling point, or boiling point. So, and that probably is hydrogen sulfide, I guess. So why oxygen and hydrogen together give rise to a very peculiar scenario where you can have hydrogen bonding, whereas this H2SE, H2TE, they might be toxic actually, and because of increased van der Waals forces something happens, and somehow H2S happens to have the least bond. I'm just giving you a scenario. So in that case, something called hydrogen bonding pretty much throws a spanner, so to speak, into the works of the machine. And that hydrogen bonding question, the question which is actually based on hydrogen bonding, should probably be a part of group 16 or oxygen family or p block elements. But in many books they find mention in both chapters, as well as chemical bonding, as well as that chapter as well. So when you have this kind of a scenario, then probably you don't have the benefit of what comes later, and that might overwhelm your understanding of this chapter, and you might think that you're not good at chemistry. So the point I'm trying to make is that even if you don't understand it all right now, probably you will get better. Perhaps it will become easier with time and practice. But to start with, you may not get it all, but that is no reason to actually get disheartened. Yeah, that's the point I'm trying to make. So I'm just going to divide it into important sections. So let us call this section 1. So I'm going to group a different many ideas into this one bucket. I'm just going to encapsulate it here. So basically different types of bonds. So you have covalent bonds, ionic bonds, metallic bonds, special case of hydrogen bonds, and how different kinds of van der Waals forces are mentioned, one of them being hydrogen bonds. So all these things, they come into play, and this is probably the starting point of this chapter in terms of developing a solid grasp of concepts. So this is where the real chemistry starts, when you get into these bonds, and when you look at different chemical species, chemical compounds or ions, and you are able to figure out that okay, potassium cyanide, potassium is it's a cation, cyanide is the anion, whereas carbon and nitrogen in that cyanide anion, at either end there are there is a lone pair, and it has both sigma bonds, it has 2 pi bonds. One pi bond is perpendicular to the other because of the way p orbitals are. So there are too many disconnected ideas, and this is just one chemical compound called potassium cyanide. The fact that it is ionic, you put it in right kind of solvent, it will break into K plus and Cn minus. From there Cn minus can be a weak base or a nucleophile, and it can just it can just bridge into seamlessly, it will just flow into organic chemistry from there. So this is just one example. So you start with one compound, and there are just so many tangents that it can take. Yeah, so it all starts with your understanding of bonds. So K plus Cn minus, ionic compound, it is soluble in some compounds, it is not soluble in some compounds. What kind of solvents will actually solvate this particular compound, and the kind of bonds which is there in K plus and Cn minus. I just gave you an example there. So next step, probably the different scales of electronegativities, Pauling being the most important of them. And there are some numericals for an inorganic chapter, for what is largely considered to be an inorganic chapter. Some people do consider it to be part of general chemistry or even physical chemistry, but even in my opinion, I think it is actually an inorganic chapter. But for an inorganic chapter to have actually numericals it's a bit of an exception. So calculation of percentage ionic character, shielding effect, effective nuclear charge, effective nuclear attraction, so that kind of a thing comes into play. So those numericals from this chapter are also important. There is another kind of a numerical which I'll come to later, but yeah, for now it's this. And maybe this is the time to actually create a notebook or a record. It could be an online or a digital record or a notebook. Good old notebook is just just good enough as well. So probably you should make a list of the ionic compounds that you come across, the covalent compounds that you come across. Store or archive this information in a way where it is easy to actually retrieve, where it is easy to revise, and through your journey of chemistry, you will come across plenty of compounds, and it kind of gives you a better understanding when you can look at one particular chemical species and think about it in many different ways. That helps develop a far deeper understanding and even appreciation of the subject that is chemistry. So make a list of ionic and covalent compounds. Simple. Next up, one of the most important topics happens to be a dipole moment. So polarity in in a covalent bond, and overall, for instance, carbon tetrachloride or CCl4. So there is a carbon, it is tetrahedral, and chlorine, despite it being very highly electronegative, despite the 4 bonds being very polar in favor of chlorine, but because of the geometry, because of the structure, the dimension of the molecule that is there, so all the vectors will actually cancel out to 0. So it is actually a non-polar molecule which has a lot of polar bonds. So this kind of distinction is very important. The understanding of polarity, the differences between electronegativity, and what kind of effect, how it spills into other areas of chemistry. That is the point I'm trying to make. That's also very, very important. So obviously polarity, covalent nature, it spills into the concept of dipole moments. And once again, when you talk about dipole moments, we have something called an instantaneous dipole moment, we have something called a permanent dipole moment, and so on. And of course, CCl4 is non-polar with polar bonds. So what about polar molecules? What kind of shapes and structures they have? Can BCl3 or BF3 ever be polar? Yes, so that becomes very important. So NH3 is polar. Is the definition of polarity even valid for an ion like NH4 plus? So that is something to think about. The whole point of polarity is just to see how the electron cloud is skewed in a covalent bond. Yes, so these different ideas, approaches to understanding the concept, that is also very, very important. So yeah, at a very basic level, chemical bonding is important. That is the point I've been trying to hammer so far. Next up, in section 2, we move on to something called hybridization. So why do we need hybridization? What is the need for hybridization? What are the different theories? So if you look at from the days of Hitler-London model, from the days of Lewis structure, you have which a form of chemistry developed into something called valence bond theory. There are 2 competing theories to explain the bonding or nature of bonding in chemical species. One is valence bond theory, and the other is actually molecular orbital theory. We'll come to that in a bit, but right now let us stay put with hybridization. So once again, the need for hybridization, what are the benefits of hybridization? Is hybridization a real phenomenon where you actually can observe hybridization happening? Is it a real thing, or is it just a concept on paper? That kind of a distinction is supremely important. I have lost count how many times people have nurtured this idea that okay, they are just going to take up a couple of orbitals, going to whip it up, and something comes of it. Yeah. So is it real, or is it a complex? Is it a theory that that actually explains a lot of real world results? That distinction, find out for yourself. Okay, that I can go on to it for hours, but please do it yourself. So sigma bonds, pi bonds, strength of these bonds, how they are oriented in space. When you look at a molecule, immediately you should have you should think of it spatially, how the different aspects of that particular chemical compound are scattered in space. Or rather, imagine you have one molecule and another molecule coming close to each other, and if you actually play around with these structures, what would happen to their electron clouds? So developing an understanding of this line is actually pretty important. Most of you, I'm pretty sure, you have gone through your books and you see 2-dimensional pictures, but it's not as helpful as I would say a 3-dimensional picture is. And and I've always seen that many people are lazy to remember the electronic configurations of the elements concerned. So do not be lazy, don't take shortcuts, because if you don't practice meticulously right now, then probably in a high pressure scenario you are likely to make more errors. And don't forget, we are preparing for a competitive examination, never forget that. Next up, as part of this section 2, get your basic terminology right. Terminologies like electronegativity, electron gain enthalpy, electron affinity. Pretty much I'm basically saying the parameters that you measure in terms of a chemical species, what kind of yardsticks that you develop. Like electronegativity is one yardstick, electron gain enthalpy, electron affinity, all these things, they are basically different numbers that help you understand a particular atom or species or even molecule. Okay, and lastly in section 2, probably hypervalence species, or what is popularly called as expanded octet. So sulfur hexafluoride and H2SO4, the sulfur atom in H2SO4, phosphorus pentachloride, there are any number of examples. So what is special about them, and the different orbitals, how they are involved, the availability of a vacant d orbital. Now this is not a very important contemporary chemistry concept, but you are tested regularly in this. And for instance, SO3, so the bonding in SO3 is probably explained initially, at least, using the availability of vacant d orbitals, and that is actually given as the primary reason why you can actually go beyond what should be an octet. We say that attaining an octet leads to stability, but in some cases, because of the availability of vacant d orbitals, is why some atoms like sulfur in H2SO4 or SF6, or for that matter phosphorus in phosphorus pentachloride, can actually expand their octet. So just keep these things in mind. This chapter definitely gives you a logical framework to be able to approach different parts of chemistry, but having said that, it's also your attention to detail and how you process data, how you process information, and try to piece different parts of a puzzle together. So slowly, right now you have one part or several parts of jigsaw puzzle here and there, but as they fall into place, then you actually get a bigger picture, you get a nice perspective eventually. But yeah, that comes with patience and persistence. Next up, for section 3, we deal with the valence shell electron pair repulsion theory. Pretty much everybody who hates approaching hybridization from first principles, they take refuge in VSEPR theory, and VSEPR is a lifesaver for those people who actually do not have the patience or a methodical, meticulous approach, or for that matter the rigor to approach hybridization as a concept, starting from those orbital diagrams, and where you draw electrons, you fill electrons according to Offer principle, Hund's rule, and Pauli's exclusion principle, and then based on other information, you whip up a case scenario where it is feasible for a particular hybridization to happen. So people who don't have that kind of patience can actually take refuge in valence shell electron pair repulsion theory. But VSEPR is a very powerful tool. There are some advantages, there are some disadvantages. There may be some exceptions where VSEPR may not always give you very good results. Some xenon compounds may be. So do understand the limitations of each and every method, and do not ever ignore the postulates, because probably people who have already taken a look at the previous year, at least the last 2-3 years JEE advanced paper, would readily conclude that gone are the days where you are only tested for numericals or tough concepts. They make it tough by making you to by getting you to make a lot of decisions in a very short duration. The more the number of decisions that you have to make per question, the likelier that you will make an error. So on that count, they are actually trying to make the exam a little tougher, which is why you have match the followings with 3 columns, match this with things from the other end, or even if it is 2 columns, just one entry can actually be matched with multiple things on the other column. So this is because they are trying to get you to check how widespread, what kind of coverage you have in terms of chemistry, not just depth, in terms of what kind of coverage. Probably their idea is to pick out that particular student who spent that extra time, who went to that extra mile trying to find some obscure fact about oxygen being paramagnetic, or a different kind of oxygen where both the electrons in the molecule do not share the same spin. Yeah, or somebody who knows carbines inside out, so those kind of people should be awarded, and probably in that with that intention, maybe they make it really tough. So keep your depth as well as breadth covered in terms of this chapter, which is very important, which is why I say that maybe in the first month or so your understanding may not be that good, but over a period of time you have to constantly keep in touch with this chapter, because this happens to be one of the cornerstones, one of the bedrocks of chemistry. So never fall out of this chapter, keep practicing, and probably there are many aspects in this chapter where you have to use your memory, your observation, and your note-taking abilities, which is why I keep hammering on the point, which is why I keep underscoring or highlighting the point that you have to make your own notes, make your own ledger of data, where you have ionic compounds, covalent compounds on one side, you have amphoteric oxides on one side, you have different types of oxides, you have acidic oxides, amphoteric oxides, the doubtful ones, and you have basic oxides, you have neutral oxides. So many different oxides are there, many different sulfides are there, some of them soluble, some of them insoluble, but until you actually make a note of these things, then it is going to be really difficult to be able to crack those integer based answer questions where they give you 10 species from which they ask you to figure out which sulfide is black, or that kind of a question. So there is no way until you have a good deal of breadth, good deal of coverage in terms of how wide your knowledge is. So, but having said that, when you're trying to do too many things, when you're trying to observe too many obscure facts, you're likely to make mistakes and forget. Probably you've seen that elsewhere and you've actually forgotten it long back. So in that case, keeping a journal really comes in handy. So coming back to VSEPR, go to the postulates, understand the postulates, and understand why it is valence shell electron pair repulsion. So when you say electron pair repulsion, you have lone pair, you have bond pair, what kind of interactions they have. For instance, if it is SF4, why is SF4 having the seesaw structure, or why does I3 the whole minus have a linear structure, or why ICl3 or Cl3Br has that kind of that T structure, and not why. Basically you could have it in such a way that there is a central atom, there are 3 ligands in a trigonal configuration, and there are 2 lone pairs upside down. But instead of that configuration, which is very logical, so mathematically it's very appealing because it's symmetrical, and we like symmetry, we love symmetry. So but symmetry is not what happens in the actual structure, which has been conclusively proven. Yes, so why is that structure more accurate or more real? Why is that structure more stable than the otherwise unstable symmetrical structure? So if you go into the actual reason and work from first principles, then you develop a solid understanding. But with practice, you should come to a stage where whatever compound is given, you should just be able to simply see it. I mean, if it is Cl3Br, I can see the molecule right in front of me, I can play around with it. So that kind of familiarity and practice is really important. Sometimes there are exceptions, so the only way to keep track of them is to make a note of them. It may not be always logical. So I would say that at least now inorganic chemistry has largely been made into a logical domain. Earlier it was just too many scattered things. So having said that, there are plenty of things which won't fit into your logic, things which don't fit into a proper logical framework. Don't try to actually push them into a logical domain, because your logic fails. There is a reason why alpha principle fails after a particular atomic number, or why there are some exceptions. So maybe they are not logical, you don't understand them, but eventually those people who pay attention and who retain that kind of information, who have a knowledge, who have a better knowledge, they tend to be rewarded better, and it is, I think, fair, is it not? So keep that in mind. And see, as far as VSEPR is concerned, it's very simple. You have a certain kind of formulae, you have a particular kind of geometry, and so make a list of pretty much everything which has a pentagonal bipyramidal structure or a trigonal planar structure. and see how many of them are Lewis acids, how many of them are, of course you won't have them, very rarely that it would happen that they are Lewis bases, but yeah. So there is a humongous amount of data, too many chemical compounds and many chemical species. For instance, you should be able to connect between I3 the whole minus and ICN twice the whole minus. Since Cn minus is very similar to I minus, or pseudo halogens or pseudo halides, that kind of a relationship. So I with all the lone pairs, and ICN with the similar kind of lone pairs, they have the same structure. So you should be able to put 2 and 2 together and see that Cn does the same role as the other I in the other compound. So this kind of making connections is supremely important, and this is likely to hold you in very good stead as far as this would augur well for you in terms of your ability to solve questions very quickly. So with enough practice, probably you should reach a place where almost anything in chemical bonding except maybe tough numerical should be you should know it like the back of your hand. I mean, it should be as simple as that. Without putting pen on paper, without actually having to sit and count the number of electrons, you should know what species, what molecules or chemical compounds are isostructural, what are isoelectronic, and so on and so forth. All those things you should be able to solve without putting pen on paper, unless of course it is a very tough question. Lastly, we have something called molecular orbital theory. So MOT versus valence bond theory, pros and cons, supremely important. Also pretty much everything which is there within our syllabus. So diatomic molecules, sometimes they could be homonuclear or heteronuclear. So all the Mot energy diagrams, pretty much for everything that is there in our syllabus, you should be able to instantly recall them. You should just, if you just know it is O2 the whole minus, then you should just start with, you should get a picture of oxygen's Mot diagram, and you should make that adjustment of, there are 2 paired electrons, one extra electron will actually make one of them paired, the other one is, it remains unpaired, and that kind of a thing. So yeah, that's pretty important. So in terms of energy level diagrams, everything should be an instant recall. Probably to be able to draw or to be able to compute faster in terms of calculating bond orders, stabilities and stability of species. So is C2 possible? Is beryllium Be2 possible? Or why not? Or is He2 plus possible? What could you comment on the stability of that species? So to be able to compute and solve these problems, you should be able to write the electronic configuration in terms of MOT even without drawing the diagram. So that actually puts you far ahead in terms of being able to solve questions based on bond order and bond strength, even bond length for that matter. That is very important. So postulates of MOT. So regarding the postulates of MOT and regarding the quantum mechanical implications, the theory, the dry theory which nobody really understands, gerund orbitals and the implications of psi, what exactly is linear combination of atomic orbitals. It is just a definition most people usually don't understand, but still its mathematical implication is something that we should all be aware of. And if there is a question, say more than one answer correct or match the following kind of question based on MOT, probably I think I'm expecting one of those questions in the next maybe 3 to 5 years, probably earlier. Yeah, so basic terminology like LCAO, postulates, yeah, those things are also pretty important. Also get your basic terminology right. So things like bonding orbitals, anti-bonding orbitals, and most importantly non-bonding molecular orbitals. So what are those, why they are important? And many people actually skip over the importance of Hund's rule and Pauli's exclusion principle with respect to molecular orbital theory. So it's obviously applicable here as well, but many people do not realize that. And if they ask you to probably disregard Hund's rule and come up with MOT configuration, some people tend to struggle actually. And if you know the diagram and the order in which you have to fill the electrons, probably it will become easier. I think that's that. Finally, overall, practice, keep in touch with this particular chapter for a really long time. because it's very easy to forget, especially MOTs, those flips, the lack of symmetry. One group of molecules will have symmetry, one group will not have the symmetry in terms of filling the p orbitals and p star orbitals. So all these things are supremely important. I think with that we actually come to the end of this section. Let me see if some of you actually have some questions. I'm trying to get a link to my question feed, but do you have any questions? Yeah, meanwhile, until the questions come up, probably see if you look at BRCL3. So in terms of BRCL3, I just mentioned that there is the central atom, there are 3 ligands, and there is a lone pair on top and in the bottom. This structure is not real. It has actually a good deal of symmetry. It appeals to our senses in that probably we think maybe this leads to a more stable structure because the lone pairs are as far apart from each other as possible. Whereas if the one lone pair was in the equatorial position and the other one was in the the axial position, then since the lone pairs are close to each other, then that would actually lead to more repulsion. So that is what we would tend to assume. But in terms of assumptions, maybe the symmetry does make some sense because it intuitively appeals to us. But if you actually take a methodical pen and paper approach, then you will actually see that the real structure is in fact more stable, because overall it is not just about the lone pairs, it's about the the repulsion between the lone pairs. LP repulsion is greater than bond pair lone pair, which in fact is in turn greater than bond pair. And when you take this into consideration and try to paint the overall picture, I think you are in a good place. Also, what I didn't mention through this chat is that we tend to look only at textbooks or 2D images, and trying to get or develop a 3D understanding of what goes on just by looking at a flat picture is probably not the best utilization of your time and energy. When you have access to technology like our product, for that matter, where we use VFX, we use visualization to able to help you exactly figure out what goes on in the 3D space. So when you use that technology, when you use not just our technology, not just BYJU'S app, there is plenty of resources out there in the internet as well for those who think I'm just trying to push the envelope here. Yeah, so Mr. Pratik Kumar is asking structure of PCl5 in solid state. You should actually PCl6 minus and PCl4 plus. So PCl5 is no longer PCl5. I think the question is not exactly relevant. So PCl4 plus, PCl6 minus, solid state, it's an ionic solid, so use VSEPR. So Chandan PG, he's asking are electrons of every elements are identical or not? It's a very deep question. Actually, it's a supremely deep question. Are electrons of every elements identical or not? Electrons of every element, I think we have the wrong picture of an electron. Probably we think that electron is a thing like this pen. It's gross, it occupies a particular space, you can actually feel it, something can bounce off it. So we think that electrons are also things like these, but apparently it turns out if you look at the quantum mechanical model, or rather if you actually spend some time trying to explore that idea, you will see that electron, or for that matter many subatomic particles, do not fit into our conventional understanding of point masses or particles. It's like they don't seem to be localized in one place. It's like they are just smeared all around in that space, and only when probably you force the electron to reveal itself, it reveals at one of the places inside that that 3D orbital. So probably I don't think this question would make as much sense if you develop a slightly better understanding of what an electron is. Once again, there is a question. Is the difference between elements due to the arrangement of electrons, protons, neutrons, or one electron in one atom is different from one another? Once again, this is the same question but slightly asked in different ways, especially when you're considering different elements. So if you look at the modern periodic law, basically it states that, you know, we identify an element just by the number of protons it has, the nucleus has, and by definition elements are, you know, neutral, and the number of protons are going to be equal to the number of electrons as well. So the number of electrons or the number of protons in a neutral atom definitely does, you know, decide the property of that particular element. So yes, pretty much, you know, electrons, protons, neutrons, how much of them are there and in what configuration are there, depending on the number of neutrons, number of protons, depending on the number of neutrons to proton ratio, and how many of each is there. So that would actually determine the chemical properties, not only the chemical properties, even the, you know, physical property, like, or rather a physics related property like radioactivity. I think we've come to the conclusion of this session. I think I hope you had something useful to take away from this chat. Thank you.